Okay, I'm not going to do example 4. You can read through that one. But you also have, I'm not going to rewrite all these formulas because that's a lot of wasted paper. But you have your derivatives of your inverse hyperbolics. So your arc hyperbolics. And then you have the integrals for them. And you'll see the same kind of pattern that happens when you do the arc functions and regular trigonometric functions. So if we start with example 5 here, we're still in 7.7. They want us to take the derivative of the hyperbolic tan, arctan of 3x. So using the rule, it says the derivative of this is going to be 1 over 1 minus x squared. Well, x is 3x, so that's going to be 3x squared times the derivative of whatever, and they don't have that in the problem, in the rules, but you always, it's a chain rule thing, the derivative of the junk, so we're going to have a 3. So we end up with a 3 over 1 minus 9x squared. The rules that they've given you in the book that are on page 486 in this version of the book don't talk about anything besides x. So remember that anytime it's something besides an x, in this case a 3x, you have to take the derivative of the 3x. Part B wants us to take the derivative of x squared hyperbolic arc hyperbolic sine of x. So this would be a product rule. So we take the first and then the derivative of the second, which according to my rules, the arc hyperbolic sine is 1 over the square root of the angle, which is x, so x squared, plus 1. The derivative of that is 1, so I don't have to write it, plus the second, which is my hyperbolic arc sine, times the derivative of the first, which is just a 2, oh, I forgot the x, 2x. The only thing I can do to this is I can factor out an x. This is just not going to look pretty. It's going to be ugly. And can I pull anything out? I think I would just leave it like that. We could get a common denominator, which means it's going to be square root of x squared plus 1. So I'm going to have an x squared, an x, because I pulled the x squared out. And then I'm going to have plus the 2. I'm going to stick a square root of x squared plus 1 on top. And then my hyperbolic sine. And all of that will be over the square root of x squared plus 1. My plus sign's a little low here, but x plus. And then close parenthesis. Okay, let's look at 6. Oh, now we're going to compute the area. Here's the problem. Over the interval 0 to 3, so we find area by integrating. And this function is going to be 1 over the square root of x squared plus 16 dx. And if you look at your integral rules, that is an hyperbolic arc sine with the 16 being in there, so it's going to change things up a little bit. And if you look at your rules, it says the hyperbolic arc sine, it's x squared plus a squared. So in this case, this is x, and the square root of this is 4. That's your a. So it's going to turn into hyperbolic arc sine of x over 4, because it's u over a, and then we're going to evaluate from 0 to 3. So now I have hyperbolic arc sine of 3/4 minus the hyperbolic arc sine of 0. The hyperbolic arc sine of 0 is 0, and we're just going to leave this one. We could go to our calculator and get an approximate answer for this. This guy is 0. Calculator says 0.693. Okay, that was part A. Part B, they want us to integrate 9 to 25 dx over the square root of x 4 minus x. This does not seem to match any of the formulas. So we're going to do a substitution here. We're going to let u be the square root of x, which means that du is going to be 1/2. Oh, we did this one a few minutes ago. 1 over 2 the square root of x dx. Now, if we change this out, this is going to turn into, with a lot of manipulating here, change out all your square roots and your x's. So we're going to have square root of x is u. Oh, I don't want to write it like that. Square root of x is u. You have a 4 minus, now you have an x. Well, x would be u squared. And then we got to take care of this is the du. It's underneath, square root of x is underneath. I need a 2 to go with it. So I'm sticking a 2 in here, which is underneath. So it's a 1/2, 2 on the outside. So I end up with an extra little 2 sticking on the outside here. And this is my one up here. Okay, I didn't write that really nice. This whole piece right here is my du. Because du is 1 over 2 the square root of x. So this guy right here, that's the 1 over square root of x. I put a 2 with it, so it's a 1/2, so I had to put a 2 in front. So there's my 2 in front. And then that turns into 4 minus u squared. But now it looks like an arc cotangent. Now I didn't change my values out, so let me fix this up. These should not be here. I've scribbled everywhere. Let's fix this. 2 integral 1 over 4 minus u squared and then du. So now I've got to figure these out. When x is 25, u would be the square root of 25, or 5. So this needs to be a 5. When x is 9, u would be the square root of 9, which is 3. So let's put a 3 here. And now I have to integrate this. So I'm going to have the 2 on the outside. I'm going to have, according to my rules for the hyperbolic cotangent, it says if my x is greater than or less than a. Okay, so we're going to, in this case, the a in this case is 2. And the rule says that if your x's are greater than 2, you use the hyperbolic cotangent, and they are greater than 2 because we're going from 3 to 5. So this is going to turn into 1 over a, so 1 over 2, hyperbolic cotangent, okay, and then u over a is 2, from 3 to 5. And so now I have to plug and chug, and I get this, the 2 and the 1/2 cancel, so I get the hyperbolic arc cotangent of 5 over 2 minus the hyperbolic arc cotangent of 3 over 2. That's an exact answer. And with plugging it in, they turned it into hyperbolic tangents in the book. But if you get it into your calculator, if you've got one that does this, you get negative 0.381. What they did was they changed the hyperbolic cotangent to hyperbolic tangent of 2 over 5, since they are reciprocals, and 2 over 3 for that one, which leads you to that answer. Now, on an 84, to give you an idea how you find this, there's no button on the calculator that I can find that finds a hyperbolic, but if you go to the catalog, so you're going to go to second and then the 0, because you're picking catalog. And then you type the letter T, which would mean just press the number 4. So T, because T is highlighted in your, when you go to the catalog, you're automatically in alpha, and you can scroll down and you can find the hyperbolic arctan. I had a hard time saying that in the right order. And then it pops up with a parenthesis and you can stick in your numbers. So you can put this in your calculator, but the 84 only does sine, cosine, and tangent, so you're going to have to convert them. That's why they went to tangents before they did that one. But I went and looked for it so that I could tell you where it was, and that's how you find that. Example 7. Now this is a word problem. I think it's kind of lengthy here. But you have to read it. You've got a length of a catenary, and so they're telling us it's the rope that's tied on both ends over like a cavern, and it makes a parabolic looking shape, but it's not really a parabola. They're giving us the function 200 hyperbolic cosine of x over 200 as its function over the interval negative 50 to 50 because they placed an xy axis in the picture. And the question is, find the length of the rope between the two anchor points. So that's arc length. So remember arc length, the formula for arc length was integral from a to b, the square root, and this is from section 6.5, 1 plus the derivative squared dx. So I need the derivative. So f prime of x is going to be 200. The derivative of hyperbolic cosine is hyperbolic sine of the x over 200, but then the x over 200 is the junk, and you've got to take its derivative, and that would be 1 over 200. So that's going to cancel with the 200 in front, and my derivative is just hyperbolic sine of x over 200. So my arc length, negative 50 to 50, square root of 1 plus hyperbolic sine squared x over 200 dx. Now, since it's symmetric, the way they've placed it on the axis, we can make this a little simpler and put a 2 out in front and go from 0 to 50. And that's the problem I'm trying to work now. And I could actually pull out the 200 by changing variables. So we're going to let the u be the x over 200. So du would be 1 over 200 dx. And now we need to substitute in. So this turns it into 2 integral square root of 1 plus hyperbolic sine squared of u. And what do I need here? I need to stick in, I didn't check that, I need to stick in a 1 over 200 to get my du, which means I need to stick a 200 in front. So this now makes this a 400. Let me see if I can fix this. 400. And du. Now, we had the main identity for hyperbolic trig functions was hyperbolic cosine squared of u minus hyperbolic sine squared of I got the square in the wrong place. Of u is equal to 1. So if I solve it, hyperbolic cosine squared of u is equal to 1 plus the hyperbolic sine squared of u, which makes that really convenient because then this piece right here turns into hyperbolic cosine squared, and the square root of that is just hyperbolic cosine. So I now have 400 integral hyperbolic cosine of u du. Now I need to change those variables over because I didn't do that. So over here, I'm taking from that information right there. When x is 50, u is going to be 1/4. And when x is 0, u is going to be 0. So this is going to be from 1/4 to 0. And now this turns into a nice simple problem. The integral of the hyperbolic cosine is the hyperbolic sine. So I'll go underneath. So this is going to be 400 hyperbolic sine of u, taken from 0, 1/4. And so that gives me 400 hyperbolic sine of 1/4 minus hyperbolic sine of 0. Hyperbolic sine of 0 is 0. So I just have to do the 1/4. And again, I can go to my calculator and put that in there, and it gets, times the 400, approximately 101 feet. That completes number